Start chapter 7. This unit is also two chapters, 7 and 8, which is the skeletal system and joints. So the bones of the skeletal system are the organs of the skeletal system. So each one is an organ, and remember that organs are made of tissues. So there's bone tissue, there's going to be cartilage, connective tissue, and then blood and nervous tissue as well. They are alive, contrary to many people's thoughts. It is living tissue and it is multifunctional. Of course, it is for movement. That's normally what we think of, and support and protecting our organs like our brain and our heart and our lungs. But it also makes blood cells and stores minerals such as calcium and phosphorus. There are two divisions of the skeletal system, the axial and the appendicular skeletal system. The axial is named after the axis, like what the world revolves around, and so it's just the middle portion of the skeleton, and then the appendicular skeleton are the appendages coming off the axial skeleton. So that's going to be like your arms and your legs. Now, they do describe bones by their shape and their size, but they all have similar structure, function, and how they develop. So there are 4 bone shapes. There are what you probably are, when you think of a bone, you might think of a femur or a humerus, but those are long bones, and they have kind of expanded ends. They are longer than they are wide. Short bones are kind of cube-like, where their width is about the same length as same length as their length. Their width and their height are the same length. Goodness gracious! Now there are sesamoid bones that are kind of rounded, and that's going to be like your kneecap, the patella. There are flat bones. Your skull are flat bones. Your ribs are flat bones. The scapula's kind of a flat bone, and it's just plate-like, so it's very broad. And you don't think of the skull being broad, but each piece of bone, there's many bones of the skull, and they're held together by sutures, but they're really, really flat. Irregular bones are all kinds of crazy shapes. We have some in our facial bones we'll see in a little bit. Your vertebrae are very odd shape bones, just to name a few. So here are some examples. A is your long bone. B is an abnormal bone. C is a flat bone. That's the temporal bone. D is a vertebra. And that sesamoid bone is the patella. E. So a lot of your test is actually naming bones for sure, but naming the parts of a long bone. And so here are all the terms you should know for the test. These are pronounced epiphysis, which epi, we've heard that so many times, is on the upper end or on top of. So this is the expanded ends. Diaphysis, dia means to go through, like your diaphragm goes all the way through you, or the diameter goes through a circle. Diarrhea, things flow through you. So that's the bone shaft, the longer part of the bone. We don't talk about the metaphysis very much, but it's just where it starts to widen to become the epiphysis. Remember, we talked about articular cartilage. This is going to cover the epiphyses, the very ends. It is hyaline cartilage. Peri, around, ost, bone. The periosteum is around the bone, and it is connective tissue, dense connective tissue. You have 2 types of bone. There's compact or cortical bone, and then spongy or cancellous bone. We'll use compact and spongy as our terms. And the compact bone we'll find in the wall of the diaphysis majorly, and then spongy bone we're going to see in the epiphysis. There will be a little bit of compact bone, but mainly epiphysis is made of spongy bone. Trabeculae are the little bony branching plates that make up spongy bone. The medullary cavity runs through the diaphysis, and that's where you're going to find bone marrow. The medullary cavity is lined with endosteum, so inside the bone. And bone marrow is found in that medullary cavity as well as in the cavities in the epiphyses, and that's where you're going to find red and yellow marrow. And red marrow will find mixed blood, and yellow marrow is mainly fat. So here are all those terms and where they're at. And so this is the epiphysis, and this long part is the diaphysis, and then you have another epiphysis here. So we have a proximal and a distal one based on where they attach. And then surrounding this is this dense connective tissue called periosteum. The endosteum is going to be inside this cavity. See this space in here? It does have some blood vessels in there, but there's also yellow marrow in this medullary cavity, which is lined with the endosteum. So you can barely see this, but it's mainly compact bone, the length of this, but this has a little bit of compact bone on the outside, but mainly it's spongy bone, and that's where you're going to find red marrow where blood is made. And then where's the cartilage? This white material is the hyaline cartilage that protects these bones ends because they're going to articulate with another bone, and we don't want bone crushing bone. So that is the macroscopic structures. We're going to look at the microscopic structures. So when you look at bone, where the bone cells, remember cyte means cell and osteus bone. So these are mature bone cells, and they live in these little lakes called lacunae. We saw this, that the chondrocytes in our cartilage also were in lacunae. And these are just holes or little lakes where the osteocytes will reside. And then there's tiny canals, canaliculi, that come off of the lacunae and actually connect with other canaliculi of other lacunae so that nutrients and waste can travel. And the extracellular matrix of the bone is mainly collagen fibers and inorganic salts. And the collagen gives it the resistance and resilience, and the salt makes it very hard. So when you look at the microscopic structure of compact bone, it looks a little bit different than spongy bone. Compact bone, we actually saw in our microscopic view. It has these, it looked almost like tree cookies or tree rings. Those are called osteons, and they have these layers of matrix called lamella. So all these rings are lamella that surround the central part of the osteon called the central canal. And within that canal is where you've got nerve fibers and blood vessels running through. It is super strong, it is weight bearing, and it does resist compression. Now, spongy bone has those trabeculae, and it's a little bit flexible, not too much, but it's still pretty strong. And the space in that trabeculae help reduce the bone's weight. So we can look through, this is a cut through a diaphysis, and you can see there is some spongy bone, but there's a lot of compact bone compared to the epiphysis, where it's pretty much all just spongy bone. There's a tiny thin layer of compact bone around the edge. And this is a flat bone of the skull, and you see there's spongy bone kind of sandwiched between compact bone. And so here is what I was talking about, those tree rings, and we call that an osteon. And this osteons are only found in compact bone, okay? So associate those words together. And so you can see here's a half of an osteon, another piece of an osteon, but here is one, and it's made of these rings called lamella. And you can see these little dots in here. Oopsie, sorry. These little dots, those are the lacunae where the osteocyte is living. And here you can see it's got like a blue nuclei in it. And these are the little canaliculi that branch off of the lacunae, and nutrients and waste can be passed on along there. Let's see. Oh, if you look through the central canal, I told you there's nerves, so that's yellow, and then the blood vessels, the arteries and veins. And so this is down the central canal. And what you notice is the central canal of this osteon and the central canal of this osteon are actually all connected. And this would be called a perforating canal because it breaks through the compact bone. And this is a little bit of what spongy bone looks like, lots of space. And these little pieces branching off to connect with others are called trabeculae. So bone has quite a few functions. We've already mentioned them. And let's just go into more detail on how they help. So they provide shape. They provide support for your body weight. They protect important organs. It says the bones of your rib cage and your shoulder girdle protect your heart and lungs. Your pelvic girdle is going to protect your internal reproductive organs and your lower abdominal organs. And then, of course, bones provide a place for muscles to attach so that you can move around. Hematopoiesis is the science word for blood cell formation, and this happens in the red marrow. Remember, red marrow is usually found in the spongy bone, and so hematopoiesis makes blood. Whether it be red blood cells, white blood cells, and platelets, they're all made in the red bone marrow, and this is why you hear about people with a blood cancer needing bone marrow transplant. It says with age, some red bone marrow is replaced by yellow bone marrow, and that yellow stores fat. So the yellow doesn't make blood. But if you've ever eaten at like a really fancy restaurant, sometimes they have on the menu that there's marrow, and they will cut you a piece of diaphysis, and you'll eat the marrow, and it's just very fatty. It would be umami if you know your flavors. Red marrow remains in the adult skull and ribs and sternum and clavicles and vertebrae and your hip bones. And bone marrow transplants are used to help treat different conditions. So those inorganic salt storage, about 70% are inorganic mineral salts of the matrix of the bone. And it's made of these crystals called calcium phosphate or hydroxyapatite, but they also have magnesium, sodium, potassium carbonate. Osteoporosis, most people have heard of that. That is where you have lost bone, and so your bone mineralization goes away, and that makes weakness and easier to break your bone. All of these calcium salts are able to be brought into the bone and released through the bone through hormones. And you've got to have calcium for nervous system and muscle movement. So you're going to have blood calcium all the time. And if your blood calcium gets too low, your body will take calcium from your bones and put it into your blood so that your muscles and your nerves can function. If you have too much blood calcium, remember homeostasis, we will take that calcium out of the blood and put it back into the bone. And those two hormones are PTH and calcitonin. Calcitonin is the one that makes calcium go into the bone. I remember that because calcitonin in, so calcium goes into the bone, and PTH allows calcium to leave the bone and go increase the blood calcium levels. And so here's our negative feedback. If your blood calcium levels get too high, there are receptors in your thyroid that sense that, and they release calcitonin. Calcitonin talks to the osteoblasts. We'll learn about those in a minute. And they start depositing calcium into bone and taking the calcium out of the blood. So what does that do? that lowers the blood calcium level back to normal. But what if they overwork? What if they take too much calcium out of the blood? Now your blood calcium levels are too low. Well, the receptors in the parathyroid sense that decrease, and they release a hormone called parathyroid hormone, or PTH. It talks to another type of cell in our bones called osteoclasts. Osteoclasts actually break down the bone and release the calcium into the blood, which returns the blood back to normal. And so you're constantly in a flux, trying to maintain those levels of calcium in the blood. So parts of the skeleton do begin to develop in the first few weeks, but remember that we started off as a cartilaginous skeleton, and bone replaces that cartilage, and it's one of two ways. The intramembranous bones, so that intra between membrane, those are going to be like flat bones, and then endochondral bones, the ends of cartilage. So it says the fetus at 14 weeks of development shows growth of both these bones. Intramembranous, I mentioned, like flat skull bones, your clavicles, your sternum, and some of your facial bones. And this is going to form, the important part here, you might want to star this, is it forms within sheets of primitive connective tissue. So your bone's going to be in sheets like this. Remember we saw like a picture of spongy bone sandwiched between the compact bone? That's intramembranous bone ossification. Endochondral ossification is going to be the long bones. So most of the skeleton is going to develop this way, and they are coming from the hyaline cartilage models. Osteogenesis imperfecta, osteobone genesis create imperfect, is a hereditary collagen defect. And so your bones are very brittle, and the fetus can actually be born with bone fractures, and you might call this brittle bone disease. And so here is a fetus, and you can kind of see some of those flat bones of the skull forming, and these long bones forming as well. But most of the body is still, or a lot of the body is still cartilage. And then if you look close right here and right here, we already have some fractures in the developing fetus. It's kind of sad. It is sad. Intramembranous bone. So let's just talk about those sheet-like layers of connective tissue where we're making broad, flat bones. So here's what happens. Embryonic connective tissue is going to be used to make these bones, and mesenchymal cells are the primitive tissue that start changing into osteoblasts. The osteoblasts, blasts usually means like to develop, and so these are bone cells that start making the bone matrix and developing kind of like a little lacunae around themselves. When they're completely surrounded by the matrix of the bone, those calcium salts, they now have their lacunae. And then that mesenchyme that is on the outside forms that periosteum. So they're showing you this is actual an osteocyte, and here is the matrix that it's made. It's in this space, the lacunae, and here's actually a canaliculi coming off of the lacunae. So here's a picture of these ossification center of these flat bones developing. So you can see some osteocytes here, and they are just laying down tissue around them. And eventually we're making some spongy bone with the trabeculae as they branch out. And then you've got your developing periosteum from the remaining mesenchymal cells. You don't need to know a ton about this, except that this progenitor cells turn into osteoblasts. The osteoblasts build bone around them, and then we call it an osteocyte once it's completely surrounded. And then actually, like, some osteoclasts break down the bone to help create this space in the spongy bone. The endochondral bones begin as these masses of hyaline cartilage. So we mentioned this is going to be most of the bones of the skeleton. And what happens is the bone tissue is replacing the hyaline. So the chondrocytes are cartilage cells. They start to enlarge, and a lacuna is developed. And then as the matrix starts to break down, the chondrocytes die, and an osteoblast, remember that's going to be a bone cell that builds, invades that lacunae that was made by the chondrocyte. And it starts laying down the bone matrix around instead of the matrix that was cartilage. So the osteoblast keeps working, and it forms spongy and then compact bone. And once it's encased, it's in its lacunae, and it's fully developed, it is now called an osteocyte. So this is kind of talking about the primary ossification center. That's an area in the center of the diaphysis where that bone tissue, we first start it to develop, and it starts working its way out towards the ends, towards the epiphyses. And it says the osteoblast from the periosteum, remember that's around the bone, deposit compact bone around that primary center. So that's how we kind of get it started. The secondary ossifications are at the epiphyses, where the spongy bone forms later in development. Now, even after you're born, your bones are still growing at the epiphyses, and you'll know that because there's evidence of cartilage remaining there called the epiphyseal plate. And that is those ossification centers, those secondary ossification centers that are still remaining and still depositing bone. So here you can see you were once just this cartilage bone, and the chondrocytes started producing their lacunae, and osteoblasts invaded those areas where the chondrocytes died and started laying down bone, and it starts developing, and the periosteum is being made. So this is kind of the primary ossification center, and it just works in both directions, and we're growing at this epiphyseal plate, and so this bone's just getting longer and longer. In adulthood, when the bone is finished growing, you don't have an epiphyseal plate anymore. You have a little remnant. It's compact bone. It's been totally calcified, and you have now what's called an epiphyseal line. So a lot of times if a young person breaks their leg or another long bone, the doctor will do an x-ray and not just look at the break, but look at, is there an epiphyseal plate? Because let's say you broke this piece, you don't want to put hardware in here that connects it to the diaphysis if this is still going to be spreading apart. And so they're looking to see, is there a line or is there a plate? And so here's these growth plates, you might call them, or epiphyseal plates in a young person still growing. So here are the major steps of bone development, whether you're a flat bone or you're a long bone, side by side. And so pause the video and just read over those, and that might help you better understand it, and then go back and look at some of the pictures. So when we're at the epiphyseal plate, we are still growing, and it has 4 zones of growth. There's the zone of resting cartilage. So this is the layer closest to the end of the epiphysis. So the most, close to the epiphysis. And it's just anchoring the epiphyseal plate to the epiphysis. Right below that, if we're at the proximal end of the bone, right below that is the zone of proliferating cartilage. And so these are cells that are dividing. Proliferate means to make more copies. The zone of hypertrophic cartilage are older cells, and they are lengthening the bone. They are where the cartilage cells are dying, and then the zone of calcified cartilage is this thin layer of dead cartilage cells and calcified matrix. So if we look at that, we're in a epiphyseal plate, and so we have these zones where there's you can see these lacuna of these chondrocytes are just kind of resting. So this is all cartilage, and then here's the cartilage is actually dividing, and here the cartilage is getting bigger, creating the lacuna, and then here the cartilage has died, and so this is where the bone will start to be produced by the osteocytes. And what's happened is this whole section has shifted up until all of this is calcified. We're still growing and have an epiphyseal plate. Osteoclasts always break down calcified matrix, and so that's going to, remember, increase the blood calcium. Osteoblasts make calcified matrix. So the osteoblasts are what replaced those chondrocytes and built the bone. And so we can just keep growing until they're finished. And so here's an osteoclast. And so it is making the bone break down. And so the calcium is being deposited in the blood. It's actually creating this medullary cavity. And I'm not going to test you on at what age and what happens with ossification of the bones. So during development of these flat bones and these long bones, the osteoblasts and osteoclasts are constantly reshaping and remodeling them. Remember, the tissue is alive, and it happens all through life, and it happens a whole lot if you're like a runner or you work out, and they are opposite of each other. So there's bone resorption, removal of bone by osteoclasts, and then bone deposition, formation of bone by osteoblasts. And about 10 to 20% of your skeletons replaced each year. Isn't that kind of crazy? So what affects this bone development? Well, nutrition and how much sun you get, your hormones, and your exercise all are going to affect the strength and healthiness of your bones. So we already mentioned, I think, vitamin D causing rickets, a lack of vitamin D causes rickets, where you have an abnormal, I don't know if it was AMP2 or AMP1, but some people, if they don't get enough UV light, like people of dark color living in near the pole, let's say, they're not getting a lot of UV, and so they're not making a lot of vitamin D. Well, why is vitamin D important? Because it allows calcium absorption. And so if you don't have that, you could have rickets. And this is why people with dark skin who live in northern regions where there's little sunlight need to take a vitamin D supplement. Vitamin A also helps with osteoblasts and osteoclasts activity. And so if you have a deficiency in vitamin A, you won't be able to develop bone as quickly. Vitamin C helps with collagen. And if you don't have that, you'll have fragile bones. And then growth hormones tells that cartilage to divide. So GH, human growth hormone, or HGH, this is what a lot of people actually use along with steroids to help not only get their muscles bigger, but get them stronger. If you have too much human growth hormone during bone development, you could have gigantism. And if you have too much growth hormone as an adult, when those epiphyseal plates have already become lines, you could just have like one appendage large. That's called acromegaly. And then if you don't have enough human growth hormone, if you have some disease that it's not released efficiently, you could have pituitary dwarfism. So the thyroid hormone and parathyroid hormone and sex hormones all affect bone development in different ways. So it might affect the cartilage or the osteoclasts or osteoblasts and epiphyseal plates. And physical stress actually stimulates bone growth. So that's how exercise causes many fissures, and then we repair those and grow bone, and your bone actually gets stronger with exercise. And so here you can see just increased bones where muscles are attached. All right, we do want to know about fractures. Quite a bit of information here, and some test questions will be over fractures. So you can name fractures for a number of reasons, and some of you who are already in the medical field have probably heard of this, and this is review for you. But there can be a traumatic injury, a traumatic fracture, and that's an injury or spontaneous or pathological. So it happened by itself. You didn't fall and cause that. But we can also name fractures based on how they break. So is it a simple fracture, which means the mucous membranes inside or the skin is uninjured, and then the compound fracture where you see bone exposed to the outside. So here are some types of fractures, and you will want to learn these well. So star this slide. A green stick fracture is incomplete, so it's not all the way through, and it's occurring along the convex surface in the bend of the bone. A fissure is also incomplete, but it's breaking down the middle. It's a longitudinal break. Now this is a complete fracture. It's more than one piece. This is still one piece. This is still one bone, but this is many. This is comminuted fracture, and that's where you have fragments. This is the one I definitely wouldn't want. Transverse break is a clean break that occurs at a right angle, and then oblique is at an angle, and then a spiral fracture is usually due to twisting. So all of these are the complete ones, and then these two are the incomplete. So how do we repair these fractures? Well, there's 4 major steps. First, you create what's called a hematoma. And hemat is blood and oma is like a tumor. So this is just a huge blood clot, and it forms really quick after you fractured. I fell and hit my arm right here on like a corner of a wall, and I was teaching high school at the time, and by the time I got to the high school, I had this huge hematoma on my arm, and the coach was like, hey, I can pop that for you and drain it. And I'm like, no, I think I'm going to leave it there, because it kind of does cushion and lets you not injure that area anymore. And it looked kind of cool, to be really honest. So first you're going to have that hematoma, and think about a lot. You have blood vessels in your bone, so a lot of bleeding occurred, and you've clotted that up. And then you form what's called a soft callus, and it's made of cartilage. Remember, we're going to use cartilage as a model for bone. So osteoblasts invade and produce spongy bone, and then the phagocytes come and kind of clean up any debris, and fibrocartilage is produced. And then you make a hard callus, so that cartilaginous callus starts to break down the soft callus, and osteoblasts invade there and start building a calcium matrix around them, and the hard callus fills up the space. And then you do some remodeling, because sometimes like for a while I had kind of a bump right here where too much calcium was laid down, and then my bone remodeled itself where osteoclast kind of restored the bone to its original shape. So here is this hematoma, this huge blood clot that is formed. This is kind of what I saw on the outside. Mine looked way bigger than that, but I'm kind of dramatic. Here is our soft callus forming with cartilage, and then bony callus made by osteoblasts. And then we have some remodeling where we're going to osteoclasts are kind of break down this bone a little bit and get it looking good. So we mentioned about osteoporosis, and there's also osteopenia is another word for bone loss. And, this is why people, when they're elderly, they're at risk when they fall of having a fracture. And honestly, like my mom just passed away not long ago, but he was telling me she was getting really ill, and he was like, she cannot fall. Like a fracture right now, she will not be able to repair, and she'll eventually like die from this. So how do you prevent all that? Fragility fractures, you've got to exercise every day. You've got to do some weight bearing exercises. Make sure you're having a good diet. Where do you get calcium? Most people think milk, and that's true, but some people are lactose sensitive. So I'll tell you that like really dark green veggies, so greens, collard greens and turnip greens and spinach are great sources of calcium. And then vitamin D is, a little bit of sunlight, which in our area of the world, you're getting plenty of that right now. Make sure you use SPF. Oh, and don't smoke. And so here you see normal bone and then an osteoporotic bone. All right, we are going to take a break here, and our next lecture is going to be about naming the bones of the body. It shouldn't be as long as this one. So take a break, go get you some vitamin D and some calcium. Maybe get a little exercise in, and I'll see you back right here.